Hello, my name is David Murray. I'm the NIH Associate Director for Prevention and Director of the Office of Disease Prevention. I want to welcome you to Part 4, Power and Sample Size, in our course on Pragmatic and Group-Randomized Trials in Public Health and Medicine. This is a free 7-part self-paced online course presented by NIH. We provide all of the slides for each of the modules that you'll see. We provide a complete set of readings, and we provide guided activities for each of the modules in the course. Today we're going to cover Part 4, Power and Sample Size. The target audience for this course includes faculty, postdoctoral fellows, and graduate students who are interested in learning more about the design and analysis of group randomized trials. We're also interested in reaching program directors, program officers, and scientific review officers here at NIH who need to learn more about this kind of design. Participants should be familiar with the design and analysis of individually randomized trials and with the concepts of internal and statistical validity. We also want participants to be familiar with linear regression, analysis of variance and covariance, and logistic regression. The learning objectives are identified here. We expect participants to be able to discuss the distinguishing characteristics of group randomized trials and individually randomized group treatment trials, particularly how they differ from individually randomized trials. We expect participants to be able to discuss their appropriate uses in public health and medicine, and for group randomized and individually randomized trials to discuss the major threats to internal validity, to statistical validity, the strengths and weaknesses of various design alternatives and analytic alternatives, and to perform sample size calculations, at least for a simple group randomized trial. And in fact, that's what we're going to focus on today. We expect participants to be able to talk about the advantages and disadvantages of alternatives to group randomized trials for the evaluation of multi-level interventions. The organization of the course is shown here. We're on Part 4, Power and Sample Size. Now, power for group randomized trials is a difficult and complicated issue, and we could spend days or weeks talking about it. So the first thing I'm going to do is refer you to some good sources of information. Quite generally, we have to adapt the usual methods for power calculations that are used in randomized clinical trials to reflect the nested design that's used in a group randomized trial. One source of information is Chapter 9 in my book, published in 1998. We have other texts, though, that have been published subsequently, including the book by Alan Donner and Neil Klar, books by Hayes and Moulton, Campbell and Walters, and a very recent book that's just been out a short time by Moorbeek and Terenstra that focuses on power for multi-level analyses. There are also some recent review articles, and I've cited 2 of them here. Recommend all of these sources to you, and the references are shown here and available to you in the reference list that you can download from our website. All of these sources provide extensive discussions on power and sample size calculations for group randomized trials. Power is tricky. Investigators are advised to get help from a biostatistician who's familiar with these issues if the investigators themselves are not biostatisticians. I do not recommend trying to go this alone, at least in terms of power and sample size. Power for individually randomized group treatment trials is even trickier. The literature is much more limited. I offer a few references here, work by Sherry Powles published in 2008, and a more recent article that came out in 2014. So strongly recommend that you reference these materials or send your methods expert to these materials to review them if you're interested in calculating power or sample size for individually randomized group treatment trials. There are 2 penalties that we have to worry about in group randomized trials and individually randomized group treatment trials. And this is what sets power and sample size calculations for these designs apart from power and sample size for individually randomized trials. There is extra variation. That's the first penalty. Because of the intraclass correlation, which reduces the correlation within groups, we have the group component of variation that increases the variability in condition level statistics, in group level statistics, and that is the extra variation that we're referring to. If we don't deal with it adequately, we're going to have less power for a proper analysis, other factors constant. The other penalty is the limited degrees of freedom that are often apparent in a group randomized trial or individually randomized group treatment trial. Remember that the degrees of freedom for the analysis of the intervention effect is based on the number of groups. And in a group randomized trial, that may be quite limited. In an individually randomized group treatment trial, it may also be limited. And if we don't deal with it, we're going to have reduced power, others factors constant if we do a proper analysis. The paper by Jerry Cornfield, published in AJE in 1978, is a classic paper in group randomized trials. It's very short, so I recommend it to you. There are some strategies that we can take to try to reduce the extra variation. One approach is to take random sampling within groups rather than subgroup sampling. If we've randomly assigned schools, it's far better to take a random sample of the students in the school rather than sampling or collecting data just in a few classrooms. If we collect data just in a few classrooms, which are examples of subgroups, we're actually increasing the interclass correlation, where if we sample across the entire school, we're reducing the interclass correlation. So random sampling within groups is a good idea. Sometimes we can benefit by timing the measurement in particular ways. In school studies, we've seen that for many measures, the interclass correlation is lower in the spring than it is in the fall. We don't fully understand why, but this is often the case. And so I have generally tried to collect data in the spring rather than in the fall. Another thing that we've noticed in school studies is that, and this would be true in other kinds of studies as well, if we have a dependent variable where there is high within-day interclass correlation, think about dietary intake measured in a school study. Kids tend to eat the same lunch at school, especially if many of them are participating in the free and reduced school lunch program. And that's going to drive the interclass correlation up if we collect all of our data in the same school, in the same day. The way to deal with this is to spread the data collection out over time. So go back to the school on several different days, spread over a 1 or 2 week period, and that will drive the interclass correlation down compared to what it would have been. And here are references for some of these issues. Other effective strategies, and this is one that I strongly recommend to you, regression adjustment for covariates. Now this is one that we deal with at the analysis stage rather than the data collection planning stage, but it's still very useful. Interclass correlation is an example of confounding of sorts. We have characteristics associated with the groups. If we can measure those, then we can adjust for them in the analysis. These would be fixed covariates in non-repeated measures analyses, time-varying covariates in repeated measures analyses. And this is one of the most effective ways to make interclass correlation smaller. It also serves to reduce residual error, so that's another benefit. Often we can reduce the ICCs by 50 or 75% with a dramatic improvement in power. So I strongly recommend this approach to anyone who's considering analysis of data from group randomized trials. These are some strategies that I do not recommend. They have been suggested at various times, used at various times, but they have been shown to be not only ineffective, but actually dangerous. So if we use individual degrees of freedom, we're going to have an inflated type 1 error rate. If we use Kish's effective degrees of freedom, we're going to have an inflated type 1 error rate. If we base degrees of freedom on subgroups rather than the groups that we randomized, we're going to have an inflated type 1 error rate. Those are better known. The fourth one on this list is less well known. If I analyze my data with a repeated measures mixed model analysis of variance or covariance, and I'm modeling more than 2 time points in my analysis, I'm going to have an inflated type 1 error rate. It increases the degrees of freedom, but it results in an inflated type 1 error rate. So I don't recommend any of those. The best way to increase degrees of freedom is simply have more groups. More members doesn't help so much, though it will in an individually randomized group treatment trial if I only have small groups in one arm. But in group randomized trials, it's the number of groups that matters. And the best way to increase degrees of freedom is to have more groups. Sample size, detectable difference in power. So in the book that I wrote in 1998, I talked about 7 steps in any power analysis. And I think this is generally the case, whether it's an individually randomized trial, a group treatment trial. a group randomized trial. And the 7 steps are listed here. We're going to walk through each of these, but they apply quite broadly to doing sample size calculation in a variety of contexts. Intervention effects, in my work, I try to define them as 1 degree of freedom contrasts. If I do that, then the t-test is the appropriate test. It's very easy. We know what the distribution of for the t-test is. Critical values are easily obtained once I settle on a type 1 and type 2 error rate. So that helps tremendously. In my book and in other sources that you can find, we provide formulas for the variance of the intervention effect given a variety of design and analytic plans, which brings us to the 6th step, which is gathering estimates of the parameters that define the variance of the intervention effect. I want to make a point here that those estimates are best collected from data that are similar to the data that we're going to collect in our study. So we want to get estimates from a similar population, data collected using the same measures, if possible, data collected using the same or similar design, and certainly estimates that are based on a similar analysis. To the extent that we differ and get our estimates from a different population using different measures based on a different design and different analytic plan, the estimates may be no good for planning the study that we're going to do, and it's just guesswork. So it's really important to get good estimates and get estimates that reflect the kind of study that we're about to do. How do we estimate an intraclass correlation? Well, one way is to go to the literature. Increasingly, we can find intraclass correlations published in the literature. The consort guidelines now ask that investigators publish their interclass correlations, and that's helped the situation. So we can often go to the literature and get good estimates. Another way is to estimate the interclass correlation from your own data. And if you have pilot data for the study that you're getting ready to do, that can be a good source. Simply apply a one-way analysis of variance with group as the only fixed effect, and apply this formula, and you've got an estimate of the interclass correlation. If you want to try to shrink that estimate, you can adjust for covariates in this analysis, and now you have a one-way ANCOVA with group as not the only fixed effect, but one of several. And now, again, you're taking the MS between and within and calculating an adjusted interclass correlation. The 7th step is to actually calculate sample size or detectable difference or power based on the estimates that you've gathered. Step number, I'm actually going to back up a couple of slides and look at my original list. The 5th step there, developing an expression, can be tricky, but my book is an excellent source, and there are other places where you can find expressions of the variance. Gathering estimates of the parameters is perhaps the most difficult step. Very important. We talked about doing that for a moment. And then actually calculating the sample size, detectable difference, or power is fairly straightforward once you've gone to the work to figure out what is the variance of the intervention effect and what are the estimates that I can apply. In doing this, we use formulas. If I have defined my intervention effect as a 1 degree of freedom contrast, for example, the intervention mean compared to the control mean, or the intervention mean slope compared to the control mean slope, the detectable difference in a simple randomized clinical trial is shown here. And the second expression, which is equivalent to the first, is the version that you're probably used to seeing. We have the usual variance of the dependent variable, sigma squared y, divide by the number of observations that contribute to each mean, n. We multiply by the sum of the critical t-values reflecting the type 1 and 2 error rates. We square that sum. We multiply by 2 because we're comparing two means, and then we take the square root of all of that, and we have a detectable difference. So it's a very straightforward calculation. It's not iterative because nothing's going to change. We may decide that that detectable difference isn't adequate, and so change the sample size for the study. But otherwise, it's not an iterative activity. In a group randomized trial, it's a more complicated expression, at least the second one. The first one, you'll notice, is exactly the same. The variance of the intervention effect multiplied by the critical values by t, summed together and squared. The lower expression adds the parenthetical expression that we saw in the first part of this course, Module 1, the variance inflation factor or design effect, defined by the intraclass correlation and the number of observations that we're measuring in each group and are contributing to the analysis. The denominator, instead of being N, is now mg, where we have m members per group and g groups per condition. We still have a 2 as a multiplier because we're comparing two means or two slopes, and we still have our t-squared values, or the t-values, the sum is squared, off to the right. I always use the t-distribution, never use the z-distribution, because the z-distribution assumes an infinite number of degrees of freedom. That never applies in group randomized trials, and so I use the t-distribution and caution you to use it as well. If you use a z-distribution, you are not taking the penalty associated with limited degrees of freedom into account, and you need to do that. This slide and the next two that follow will help you understand a bit the role of the intraclass correlation, the number of groups per condition, and the number of members per group in the detectable difference calculation. You've seen these before if you watched part 1 in this course, where we reviewed them briefly. The lines show the detectable difference, which is on the y-axis. The lines distinguish based on the number of groups per condition. The red line that's at the top has only 2 groups per condition, so that's the smallest group randomized trial that we can run and have any variation associated with a group within study condition. Members per group are shown on the x-axis. And you'll notice in general that the lines have a little bit of curvature to them as we move from 25 members per group up towards 100 members per group. After that, the lines are pretty flat. And what that's telling us is that when we have a large interclass correlation like this, 0.1, we don't get much benefit out of having more than 100 or 150 members per group. In contrast, we get a lot of benefit out of having more groups per condition. The line with just 2, that upper red line, is quite high on the y-axis, and the lines drop as we add more and more groups per condition. This slide also shows that if you only have 2 or 4 groups per condition and an intraclass correlation as high as 0.1, you have to have a very large intervention effect to find it to be significant, because the detectable differences are quite large in standard deviation units. And you have to have a quite large study in order to be able to detect a more reasonable intervention effect. As the intraclass correlation shrinks, and here it's dropped by an order of magnitude, we get more curvature in the line. That gives us more benefit from adding members to each group. All of the lines drop, and now we can have a reasonable detectable difference, even with 16 or 8, or sometimes fewer than 8 groups per condition. If the intraclass correlation drops by another order of magnitude, the lines drop a little further, there's more curvature, and we are usually in pretty good shape, even for smaller studies. It's very important that you do your own calculation based on a good estimate of the intraclass correlation. It's dangerous to assume that the intraclass correlation is going to be as small as this, or even as small as 0.01. Much better to have a data-based estimate for the study that you're proposing. Now, let's actually walk through an example, particularly an example using the 7th step, which is calculating the sample size. If we have a 1 degree of freedom contrast between 2 means or 2 mean slopes, the sample size calculation for the number of members in a randomized clinical trial is the first expression, and the corresponding expression for a group randomized trial is at the bottom of the screen. I showed you the formula for detectable difference earlier. This is the formula for the number of groups we need in each condition. It involves the same elements algebraically, but they're rearranged to solve for G. Let's calculate the required sample size per condition for a 2-condition randomized clinical trial first, with a 5% type 1 error rate, 80% power. You've seen the formula that's used. It's the standard formula. To make things simpler, I'm going to work in terms of standard deviation units and set sigma squared y to be 1. If we substitute this expression into the formula and use a delta of 0.2, if we assume we have lots of degrees of freedom, I can use 1.96 and 0.84 as my critical values for t. Do the math, and we get a number 392, sorry, for the number of members per group. So we need a pretty large study with a modest effect size of 0.2 standard deviation units. But here's the answer, and we're done. If we want to apply this in the context of a group randomized trial, one of the things that we're going to discover is that it's an iterative calculation. And that's because the number of members per group determines the critical values, and the number of members per group appears in the numerator and the denominator, and the value that we get for G may change from one calculation to the next as we move through the iterations. Here we're going to make the same assumption in terms of the type 1 and 2 error rate, 5%, 80% for power. The same magnitude intervention effect, 0.2 standard deviations. We're going to start with, because we have to start somewhere, an intraclass correlation of 0.01 and 100 members per group. If we drop those values into the formula and do the math, the value that we get for a result is 7.8. We always round up, so 8 groups per condition. Now, we can't stop there, though, 8 groups per condition, because the t-values that we used in this expression assumed an infinite number of groups per condition. So the critical values of 1.96 and 0.84 don't hold if we only have 8. If we have 8, we can recalculate degrees of freedom. 2 times g minus 1 or 2 times 8 minus 1, 14. Now we need to go back to our t-table, look up the critical values based on 14 degrees of freedom, and drop those into our formula. 2.145, 0.868. Redo the math, we get 9.03. Now we can drop 9 into our formula for degrees of freedom. We get 16. We look up the critical values of t there, 2.12 and 865. Drop those in, do the math, we get 8.86. We can round up, we're at 9 again. At this point we can stop, because the value that we're getting out of this calculation, 9, is the same value that we use to calculate the degrees of freedom and the critical values for t. So now the critical values using the expression are consistent with or concordant with the result that we're getting, and we can stop. We can say that if we randomly assign 9 groups to each condition, we will have, given a type 1 error rate of 5%, 80% power to detect a 0.2 standard deviation effect, given an intraclass correlation of 0.01 and 100 observations per group included in the analysis. I said we could stop there, and certainly we can stop there for that calculation. We don't have to do any more iterations. But I would caution you, it would be very wise to perform a sensitivity analysis using different values of the intraclass correlation, different values of M, different values of G, to see how much the result would change as these other factors change. And you may want to present some of that in your grant proposal. I always do. Let me comment a little bit on the situation that we deal with if we have an unbalanced design. All of the formulas that I just showed you in the example that we worked through assume that every group had the same number of observations contributing to the analysis. And as long as the ratio of the largest to the smallest isn't any worse than about 2 to 1, okay, we can use those methods. If there is more extreme imbalance, though, other methods are required. You can have an inflated type 1 error rate if you use what I call the standard group randomized trial methods, if the imbalance is worse than 2 to 1. And I'm going to not walk you through the methods, but I am sharing with you here references to recent articles that address this issue, and I recommend that you take a look at them. If you're working with an individually randomized group treatment trial and have substantial imbalance in the group size, that's also been addressed recently in the literature, and here are a couple of references. We can get into difficulty here as well if the imbalance is worse than 2 to 1. So in summary, the usual methods for detectable difference, sample size, and power are not appropriate for group randomized trials and individually randomized group treatment trials. We have to adapt those methods to reflect the nested designs that are inherent in these other studies. Power is a tricky subject, and I strongly recommend that investigators who are not biostatisticians themselves work with a biostatistician. 30 years ago, it was difficult to find a biostatistician who was familiar with these methods. That is not true today. Every decent-sized campus is going to have biostatisticians who are familiar with mixed model regression, random effects models, and even if they haven't heard of a group randomized trial or a cluster randomized trial, they will be familiar with the underlying methods and can do a little reading and come up to speed on it fairly quickly. You need to address both of Jerry Cornfield's penalties, extra variation and limited degrees of freedom. It's increasingly common for people to remember the first part, but they often forget the second part, and I want to emphasize both. Often we'll see in the write-up of a paper that they used a method to account for the extra variation, but they report a z-test or a wall test that assumes infinite degrees of freedom. You need to deal with the limited degrees of freedom as well and be reporting a T or an F or something that reflects the limited degrees of freedom. Failure to do so will result in an inflated type 1 error rate. None of us want that. There are effective design and analytic methods that we can use to reduce the intraclass correlation. Regression adjustment for covariates is one of the best, but there are also some design steps that I mentioned. The most important factors affecting power in a group randomized trial or individually randomized group treatment trial are the intraclass correlation, the number of groups per condition, and so you want to have a good estimate of the intraclass correlation and have a good number of groups per condition in order to have adequate power. I want to thank you for your attention today. We've been talking about sample size and power in group randomized trials in public health and medicine. I want to draw your attention again to our website where you can give us feedback on this module. You can also download the slides from today's presentation, the references for the entire course, and you can download suggested activities based on today's presentation. You can also watch the module again if you'd like to see it and review the material. I would also encourage you to watch the next module in the series, which presents some examples of group randomized trials. If you have any questions, please send them to grt@mail.nih.gov and we'll get back to you. Thanks very much.